Okay, this video is for Milestone 4 Finite State Machine. The objective of Milestone 4 is so that we can understand the basic of finite state machine better. So what is finite state machines? Finite state machine is an abstract mathematical model of a sequential logic function with finite inputs, outputs, and number of states. So let's look at the overview of the problem. So in this Milestone 4, we need to use the same hardware setup as the nickel and dime vending machine. If you remember from Milestone 2, we have created a night rider lights, and in this Milestone 4, we have to build a combination lock which runs one round on it when the proper sequence of buttons are pressed. So what is the sequence for this project? The sequence are different from each group, and since we are group 13, we are assigned to use the NDDN sequence. Now let's look at the sketch that we have made. This is the sketch that we created. This is the Moore state machine, and this is for the Mealy state machines. And the quarters implementation will be explained after this.
Now, we choose more approach to be implemented using state machine editor in Quarters. So, this is the state diagram of using the more approach. Then, this is the simulation waveform. Okay, so when the correct sequence was detected, which is the NDDN, a complete cycle will be run. And when the done was detected, the finite state machine will reset to the initial state. So next, we make the more finite state machine to the symbol file and connect the finite state machine with the input filter and night rider. And this is the simulation waveform. So same, when the correct sequence NDDN was detected, the night rider will run around, and when the done was detected, the finite state machine will reset to the initial state. So next, we connect the prescaler to the circuit before, and this is the completion report, and it's successful. So that's all from me. Thank you.
For part 4.4, we are going to implement more FSM using one hot method, and then for easy step, we create a state diagram as shown here to get the next state equation and also the output equation. For next state equation, we are going to take each respective state here. For example, for x1 plus, we'll be taking every s1 plus here to get the complete equation. For example, for the first row, s1 plus will be equal to s1 d bar and bar in order to get the equation. The others will be the same steps. For the output equation, since the output of more FSM will be its last state, so R will be equal to S5. Here will be the next state equation and also the output equation we get from the state diagram. And then based on this equation, we created this schematic diagram. Each input here will be according to the next state equation. For example, like this one will be for S1, this one will be for S2, and so on. Since there's 5 states in the more FSM, so we are required to use 5 D flip-flops as shown here. And then to verify the schematic diagram, we are required to run the simulation output waveform. As we can see here, for the input, based on our sequence, the state will be complete when the sequence NDDN is detected, as shown here. NDDN, only this part we will have the complete sequence where the circuit is come from S1 to S5 and R is detected, as the same here, NDDN. And then after we verified this schematic diagram, we created a symbol, and then we insert into this schematic diagram here together with input filter and also nut rider. And then before we insert the prescaler, we need to verify the output of this schematic diagram. So same step. Since there are two clock input, one Hz and one with 100 Hz, we set this as 10 nanosecond, and then this will be 1/100, which is 0.01 nanosecond. Okay, as we can see here, KR will be the nut rider output. As we can see here, when the input NDDN is detected, since there's filter, so the input will be according to the filter here. When NDDN, the correct sequence is detected, S1 and S1 will be going to S5. R is detected as shown here. The nut rider will run for one round, and then after the nut rider has performed one round, done will be detected, and then the state diagram will return to its initial state and wait for the next output. And then after we verify it, we insert the same more one hot method symbol into the circuit. This time we are going to insert prescaler, and then this circuit will be programmed into CPLD to test the output. That's all for part 4.4. Thank you.
So for part 4.5, we have the state diagram of Mealy FSM that will be binary encoded to decrease the number of states and to reduce the glitches. We reduce the number of states because each state in the normal Mealy FSM is a D flip-flop. So we have 5 D flip-flops. However, when we give each state a special binary code going from 0 to 5 in binary, we only use 3 flip-flops, which maximizes the performance and reduces the glitches. With the comparison to the Mealy state diagram, we can deduce the next state and the output for each input and the present state combination. And here are the equations that we get. So with the equations of the next state equations and the output equations in hand, we can go to the schematic editor and add all the equations. So this is Q0, Q1, Q2, and we only use the 3 flip-flops. And here we have the inputs and outputs, and here we have the logic of each state, converting from binary code to the actual state to be able to track the states. So now that we have implemented all of the logic gates in the schematic, we can set it as the top level entity and simulate it. And here is the waveform file. So when we get the correct sequence in DDN, R becomes high, and when R becomes high, our design waits for when done is high, and when done is high, the states go from S5 to S1. As we can see, as we go through all the inputs, the states keeps changing. So when we have a correct sequence, the states go from S1 to S5, and if we have a correct incorrect sequence, we never reach S5, as S5 is considered as the output for the state of R, and here the sequence is repeated again in DDDN, which results in high R, waiting for done, and when done is high, we go back from S5 to S1. So after we have checked the waveform, we can now create a symbol, and after we create a symbol, we can implement it with the Night Rider and two filters to simulate a push button input from the user. Done from Night Rider is connected to the done input of Mealy, and the R output of Mealy is connected to the enable input of Night Rider. So after we compile it, this is the state. So this is are the input coming from the user. They go through the filters. The filters are connected to the 100 hertz clock. The filters give an output of one clock when after the input is finished or goes to 0. This filtered input will go through the Mealy symbol, Mealy block, and when the correct input is detected, output R becomes high, activating the Night Rider, which is KR here, and the Night Rider goes one complete round from A to F and backwards, activating done when it finishes, and done resets R to 0, and we can, if we minimize KR here, we can see the states. So these are the binary encoded states, and these are the actual states. So as we wait for the correct input, we go through the states, and when we reach S5, R becomes high, and then we wait for done, and when done is reached, we go back to S1, and here we have the correct input, and when we have the correct input, the KR is activated again, waiting for done. So that's all for my part 4.5. Thank you. This is the demo for Milestone 4, topic 4.5, the binary coded Mealy FSM. Our sequence is NDDN. So if I click NDDN, starts. If I click a wrong sequence in it does not start.